Now let's think about the plane equation. Now, before going to the plane equation, in 2D, tell me what x equal to 1 is. If you have this equation, what does it represent? It's a line. It's a vertical line, right? Why does this represent the vertical line? Can anyone explain?
It goes through point 1 on the x-axis.
Yeah, I think the, yeah?
For every y, the x value is 1.
Right. So that's better. So this is basically saying that I don't care about the y coordinate, the x coordinate has to be 1. So if you think about the entire two-dimensional plane, and you pick all the points whose x coordinate is 1, you get 1, 0, 1, 1, 1, 2, 1, 3, 1, -1, 1, -2, 1, -3, 1, whatever, and you end up with this line. That's why x equal to 1 represents a vertical line, right? Now the next thing to ask yourself is, in 3D, what would this be then? In 3D, x equal to 1 represents what?
The axis?
It'll be a plane, right? What kind of plane? It's a plane parallel to what? Okay, so let me give you a multiple choice. Plane parallel to xy plane, yz plane, xz plane. Which one is it? YZ plane. It'll be a plane parallel to YZ plane, okay? Now, let's think about y. See, this is x, that's y. Now, think about z as coming out from the board. You're basically collecting all the points in space whose x coordinate is 1. So it's basically 1, 1, 0, 1, 2, 3, 1, something, whatever. Whatever you're picking, that the point that you pick should have the x coordinate as 1. So it can be not only on this line, everything on this line is a valid thing that satisfies this, because this means z is 0, but you can go one level higher so that you get a z equal to 1 there. Or you could set z equals to 2, z equal to 3, z equal to 4, right? Or z equal to -1, which will be behind the board, right? And if you think about this entire thing that you end up getting, is it's a plane that's going this way, right? Which is perpendicular to the x-axis, and it's also parallel to the yz plane. That's how it works. Okay? All right. So what this demonstrates is that whatever you do in 2D that represents a line will become a plane in 3D. So let's think about another example. In 2D, y equal to x is what? It's a line, right? In 3D, what would this be? Because this says nothing about z, z has the freedom, so you can basically lift this up and continuously lift it up, right? Or make it go behind the board, and you end up with this plane that's like that. Okay. So it's a plane that is containing the z-axis, right? Which cuts the xy plane in 45 degrees this way. So that's the plane that you get. All right. So at some point, doing more and more of these examples, you start noticing that if you want to plane in 3D, in general, it will be like this. In 2D, ax plus by equal to a number, that's a line, right? Yeah. Ax plus by equal to a number, that's always a line, right? In 3D, all you have to do is add another one, another z term, right? And say it like that. That's a plane. So in 3D. In 3D. So in 2D, this is a line. And in 3D, this is a plane. And you can see that this thing actually this contains these two as a special case, right? So how would you get this from this form? What should you set A as? A is 1, B is 0, C is 0, D is 1. Then you get this equation, right? If you set A as 1, oh no, actually, if I move this to the other side, it's negative x plus y equal to 0. So if you set A as negative 1, B as 1, C as 0, and D as 0, then you get this second example. And in general, this will be a plane equation. So that's the hard thing to grasp at first, okay? Realizing that in 3D, one such equation, this is called a linear equation because all of these variables have power 1, and none of the variables are multiplied together. So one linear equation in 2D gives you a line, whereas one linear equation in 3D gives you a plane. Okay? And two linear equations in 3D gives you a line. Okay? Now think about why that's true. If you have one plane and you impose another plane, if you want these two to be satisfied at the same time, what are you looking at? You're looking at the intersection of the two. And what's the shape of an intersection of two planes? It's a line. It's a line. Right? That's why if you go back to the line equation and think about the symmetric form, it's two equations. Okay? If you look at the first equation, that's a plane. If you look at the second equation, that's a plane. And basically, the symmetric form of the line equation is saying, hey, you have these two planes, then its intersection is the line we want. That's the way you understand the symmetric form of the line equation. All right. Now, so for the plane equation, we still need to figure out a meaning for A, B, C, which is, again, kind of like the slope, but not quite, because slope in here is like you really need to solve for y, right? Yeah. A and B are not really the slope, so A, B, C is, of course, not a slope. But here's how you understand the A, B, C in the standard form of the line equation in 3D, okay? So start with the ones that pass through the origin. This type of equation passes through the origin, right? Because if you plug in 0, 0, 0, it satisfies it. So I know that this is a plane passing the origin, right? 0, 0, 0. Let's try to understand this first, and if you understand this, then this is easy to understand because once you have any object passing through the origin, if you want a plane that's not passing the origin, all you have to do is just shift it. Right? If you replace x minus x naught, y minus y naught, if you do that, you end up with another plane passing through another point. Okay? So this is the first thing that you want to know. And then you look at this formula and say, hey, this looks like pairwise multiplication you're adding. What's that like?
Matrix, right?
Not a matrix. Pairwise multiplication. Two things are multiplying, you're adding them. When did we do some dot product, right? Yeah, it's a dot product. So let's imagine a dot product that produces this. So here's what you get here. A, B, C. Dotted with x, y, z. And that should equal to 0. Okay. So that's another form of the plane equation, which although we will never use this. Okay? I wrote this down so that we will have some geometric understanding of this. Okay? We'll be using this form, not this one. Okay? Now, then think about the following question. What does it mean for two vectors to have the dot product at 0?
It's
Perpendicular, right? If two vectors have a dot product with 0, that means it's perpendicular. All right, so now let's think about what that means. It means that if you have a vector A, B, C, and here's the origin, then the points that satisfy this are all these endpoints that come out from this origin that's perpendicular to this line. So it's this plane where every point, when you connect to the origin, if you measure this angle with this ABC, it'll be 90 degrees. Be 90 degrees. 90 degrees. Okay. So A comma B comma C is what we call a normal vector. So there are many words to describe 90 degrees. So orthogonal, perpendicular, 90 degrees, right angles, they all mean 90 degrees. And in addition to that vocabulary, put this word too. Normal, in that context, means if it's 90 degrees to a flat plane. In that case, people use the word normal. So A comma B comma C is a normal vector. And in general, the equation of the line is like this. A times x minus x naught, B times y minus y naught, plus C times z minus z naught equal to 0, where x naught, y naught, z naught is a point on the plane. So that's how you write down the line, the plane equation in 3. Plane equations look like this, where A comma B comma C is a normal vector, x naught, y naught, z naught is a point on